When I was a newly minted adult and trying to learn what implicit differentiation was, I felt like every definition that I was reading felt super lofty and using the academic vocabulary that was intended to impress another academic person as opposed to just talk to a human. So this is the explanation that I wish I would have gotten many, many moons ago, but we have to understand chain rule first. So here goes. This is where we're going with it. So the old way is that you have to know what y is in terms of x, and the new way is that you don't have to know what y is in terms of x. Let's elaborate. So we have y to the fifth, but we know that y is 4x squared plus 7. So we replace that, and now let's derive with respect to x. We know what to do with the power rule. We're going to multiply that 5 in front, subtract 1 from our exponent, we have a 4. But because we had an inside function, we also need to multiply it times its chain. What's the derivative of 4x squared plus 7? The derivative of 4x squared plus 7 is 8x, and we have to multiply that to the end to chain it on there, chain rule. You could also clean it up a little bit and call this 40x times the quantity 4x squared plus 7 raised to the fourth power. So here's the new part. What if we have to derive this without knowing what y is with respect to x? We still use the power rule. We still multiply that 5 in front and subtract 1 from the exponent, but then we also have to chain it and multiply it with whatever the derivative of y is with respect to x. So what is the derivative of y with respect to x? Here's the magic, we don't know. So we literally just say times the derivative of y. That's the implicit part. And it doesn't matter which of these notations you want to use. Either one works. I'm going to be switching back and forth. So let's start off nice and easy and find the derivative of this with respect to x, and then solve for the derivative. Pause, and the answer will be on the next slide. How to go. Now, one of the really cool things about this is that a circle is not a function, and you are no longer limited to deriving nothing but functions. You can derive things that aren't even functions now, and that's beautiful. And speaking of beautiful, if I give you a point, you can find the tangent line at that one point, even though it's not even a function. That's kind of cool. And for more pretty, then we could leave them arbitrary and get lots of different tangent lines. Okay, now derive this with respect to x. The very first part needs a product rule, and this is implicit differentiation. The first line will be available on the next screen. That first term requires a product rule, so it's the first times the derivative of the second, so x times the derivative of y cubed. That's going to need an implicit, plus the second times the derivative of the first. That's why you have the y cubed, but then the derivative of x just 1. Plus 4, because we're deriving with respect to x, and that's equal to 2y prime, because we're deriving with respect to x, not y. So when we're deriving with respect to x, that feels really normal. When we're deriving with respect to x, but there's a y, then we also have to chain it with the derivative with respect to x, the derivative of y with respect to x. Algebraically, we have to solve for y prime. So anything with a y prime gets moved to one side. I'm picking the right side. So I'm subtracting over that first term from both sides. Then I factor out that GCF of y prime, and then I divide by all the stuff that is not y prime on the right side, which is 2 minus 3xy squared. So the very first line was the calculus. After that, everything else is algebra. And this part's entirely unnecessary, but just this is what the original equation would look like if you graphed it. And using the derivative that we just found as a way to find the slope of a tangent line, then you can find all of these tangent lines. I just like watching it move. It's kind of pretty. Again, this part's just for fun. But I hope that this inspires you that implicit differentiation is not as nonsensical and as boring and lofty as I saw it the first time. It can actually do some really beautiful things.